Have you ever pondered over the concept of determinism and state dependence in programming languages, especially in the context of the Tao language? Well, today we're going to unpack these ideas and look at how they play a pivotal role in shaping the Tao language. Determinism, in essence, is the idea that for every input, there's a well-defined output. This principle is the bedrock of many programming languages, and Tao is no exception. It ensures that for any given input, the output is predictable and consistent. Now, let's add the concept of state dependence to the mix. Unlike some languages where outputs depend solely on current inputs, Tao embraces a model where the output can hinge on previous outputs or states. This introduces a whole new dimension to programming with Tao, allowing it to capture the temporal nature of events. So let's delve deeper into these concepts and how they shape Tao language. Determinism is the backbone of many programming languages, Tao being no exception. This fundamental principle asserts that for any given input, there will always be a well-defined output. It's like a promise, a guarantee that a specific set of inputs will consistently produce the same set of outputs, time and time again. No surprises, no unpredictability, just reliable and repeatable results. This is especially important for software systems that are specification-driven, like those developed using the Tao language. Tao takes this principle of determinism and runs with it, but it doesn't stop there. It broadens the concept to assert that not just for some, but for all inputs, there will be a well-defined output. This extended guarantee is what sets Tao apart, and it's a key reason why this language is a go-to choice for building reliable and predictable software systems. But why is this so important? Well, when you're developing software, reliability and predictability are everything. You need to know that your program will behave exactly as expected every single time it's run. Without this assurance, you're left in a world of uncertainty and potential chaos. It's like trying to build a house on shifting sands. Without a solid and reliable foundation, everything else becomes unstable. In the world of Tao, this solid foundation is provided by the principle of determinism. It ensures that the outputs of your program are not left to chance. Instead, they are tightly bound to the inputs. Change the inputs, and the outputs will change accordingly. But feed in the same inputs, and you will always get the same outputs, no matter how many times you run the program. This deterministic nature of Tao lends itself beautifully to specification-driven development. By defining the behavior of a program based on its inputs, developers can write software that behaves predictably and reliably under a wide range of conditions. This makes Tao an ideal choice for building complex systems where precision, reliability, and predictability are paramount. Therefore, determinism plays a crucial role in Tao, ensuring consistent outputs for given inputs. State dependence introduces an additional layer of complexity to Tao programs. This concept brings in a unique perspective, where a program's output doesn't just rely on the current inputs, but also takes into account the historical states or outputs. In other words, the past matters in Tao. This approach is closely tied to the principles of temporal logic. Now, temporal logic is an extension of classical logic where we incorporate the element of time. It allows us to express propositions whose truth value can depend on time or the sequence of events leading up to the current state. So in the context of Tao, temporal logic provides the framework to express and handle state dependence effectively. Imagine a simple game of chess. The outcome of your next move doesn't only depend on the current state of the board, but also on your previous moves, your opponent's previous moves, and the strategies you both employed. This is precisely how state dependence works in Tao. It allows programs to have a sense of history, to be aware of their past states, and to use that awareness in producing outputs. This approach is quite distinct from purely functional programming approaches, where outputs are strictly a function of current inputs. State dependence in Tao allows for a more flexible and powerful programming model, where programs can adapt their behavior based on their historical context. For instance, imagine a program that manages a smart home system. The system's response at any given moment could depend on the sequence of events that occurred throughout the day. Whether the owner is home, the time of day, the temperature outside, and so on. By allowing state dependence, Tao enables such complex, temporally aware systems to be modeled effectively. But remember, with great power comes great responsibility. Incorporating state dependence means we need to be mindful of how we manage and update state information. We also need to consider how past states influence current outputs when designing our program specifications. State dependence in Tao, therefore, allows for a more dynamic and temporally aware programming approach. It opens up new horizons for creating more sophisticated, adaptive, and intelligent software systems. These principles of determinism and state dependence have far-reaching implications for the Tao language. Firstly, let's talk about specification complexity. In Tao, program specifications must account for not just the current inputs, but also the historical context. This broadens the expressive capability of the language, but also introduces an added layer of complexity to the specification process. Programmers must employ more sophisticated logic to accurately describe the desired behaviors, which can be both a challenge and an opportunity for deeper understanding and control. Secondly, there's the execution model. The Tao execution engine needs to maintain state information across execution steps. It uses this information to compute outputs based on both current inputs and past states. This requires an execution model that can efficiently track and update state information over time, ensuring consistent and accurate output generation. Next, we come to model finding and satisfiability. Given Tao's state-dependent nature, finding satisfying models, that is, outputs that fulfill the program's specifications, becomes a more intricate process. The system must consider the space of possible states and their transitions, employing satisfiability solvers capable of handling temporal logic. This complexity, while challenging, also sets the stage for more robust and comprehensive solutions. Fourthly, there's debugging and verification. These processes involve not just checking individual inputs and outputs, but also ensuring that the program behaves as expected across different sequences of states. This requires tools capable of analyzing the program's behavior over time, providing a more holistic view of the program's performance and potential issues. Next up, temporal logic and specification languages. The use of temporal logic in Tao allows for the specification of behaviors that are dependent on sequences of events or changes over time. This opens up possibilities for specifying and implementing reactive systems, schedulers, and complex workflows that are responsive to evolving conditions. It's like giving programmers a time machine to navigate the past, present, and future states of their programs. And lastly, let's look at enhanced reliability and predictability. By ensuring that all inputs lead to well-defined outputs, possibly influenced by historical context, Tao aims to enhance the reliability and predictability of systems. This approach facilitates the development of robust software that can react adaptively to its operational environment. It's like having a reliable guide in an ever-changing landscape, always leading you to your destination, no matter the path taken. So, these principles fundamentally shape how we conceptualize, develop, and execute Tao programs. We've covered a lot of ground today, discussing determinism and state dependence in Tao. So let's take a moment to summarize the key points we've delved into. First, we explored the principle of determinism in Tao, which guarantees that for every input, there's a well-defined output. This principle is a cornerstone of Tao, ensuring reliability and predictability in our software systems, especially in specification-driven approaches. Next, we introduced the concept of state dependence in Tao, highlighting that the output isn't just tied to the current input, but can also be influenced by previous outputs or states. This principle aligns Tao with temporal logic, where the truth value of propositions can change over time or based on the sequence of events. We then dived into the implications of these principles for the Tao language. We discussed how they influence specification complexity, necessitating a more sophisticated logic to accurately describe desired behaviors. We touched upon how they shape Tao's execution model, requiring an engine that can efficiently track and update state information, We also explored how these principles impact model finding and satisfiability in Tau. With the state-dependent nature of Tau programs, finding satisfying models becomes a more intricate process, requiring solvers capable of handling temporal logic. Furthermore, we discussed how determinism and state dependence affect debugging and verification in Tau. Tools for these tasks must be capable of analyzing program behavior over time, ensuring that programs behave as expected across various sequences of states. We highlighted how the use of temporal logic in Tau opens up possibilities for specifying and implementing complex, time-dependent systems. Lastly, we reiterated how these principles enhance the reliability and predictability of Tau-based systems, facilitating the development of robust software that can adapt to its operational environment. Remember, understanding these principles is essential for effectively leveraging the power of Tau for robust, predictable, and temporally aware programming.